Hello and welcome to my contribution to the IVS General Meeting 2022. My name is Alexander Neidhardt and I'm from the Technical University in Munich working at the observatory in Wettzell. And today I want to talk about the IVS Seamless Auxiliary Data Archive and the corresponding EVN Monitor. Together with my co-authors, we implemented such a data archive, and especially the EVN Monitor was also funded by the European Union's Horizon 2020 program. So today I want to give you a first current status. Then I want to talk about the benefits of this seamless auxiliary data, and I want to give a summary, and there I have some wishes. So before we start, what is this IVS SADA? So why do we do this and what is the background? So let's say that this is a data archive. This data archive is nothing more than a database with a special software running on it to prepare data, to administrate data, and let's say it is located at a special location in the internet. So our data archive is located at Wettzell under this address. I have to say at the moment that we have a network outage, so therefore this address is not accessible, but usually it's accessible. So what is the special thing here? There are data continuously, so not only session-based, which means the data are already used at the moment, but they are just in the log files, so they are specific for the different sessions. Here we have them continuously. Also, when there is no session, when there is no radio telescope observation. And another thing is that you can request these data continuously, so seamlessly. So it means you just say, I want this interval, this time interval, and you get it. And especially with these characteristics of let's say real-time data stream, you have additional possibilities. So you can detect errors directly on time and things like that. And maybe you can also use them for dynamic observations, things like that. Important for this data archive is that the data sending and also the data requesting is standardized. So let's go to the data sending. For the data sending, especially at the sites, you have a standardized interface and you don't have to install some software. So you just use software which is already available, especially on Linux systems. So you don't have to install additional things. You just use an SSH call, so it's a secure shell call, and you run a remote program on our servers called SAPIC senders, and the arguments for this SAPIC sender is the timestamp and the value, and of course the key. So the key is predefined, so these are the keys for the elementary data set. So you can send temperature, humidity, pressure, wind speed, wind direction, and also the GPS minus FM out, so clock corrections, .mon. If you run this, the data are directly injected, so you just integrate this call in your existing software, nothing more. And then the data are sent to this archive. On the other hand, you can request the data easily with predefined access points. A very important thing is that the access points are based on HTTPS, so it means it's the standardized protocol, and therefore you can use them for the web pages, so for web services, for different presentation layers, and you can use them also additionally for the seamless data access. There is a Python script, and this Python script uses this access point to request data. What is now the specific thing? So this archive is operative for a long time. There are some improvements, but what is the specific thing at the moment? So I told you something about this network outage at Wettzell, and therefore it's quite important that you have an additional one. so that you have an additional access point. Another thing is that there are other networks like the EVN, and they also want to have these access points, and they also want to have this auxiliary data. So therefore, we also implemented during this Jumping JIVE project, which was funded by the European Union, we implemented a second access point. And the second access point is located at the EVN, called EVN Monitor, and there you can also send data to. So therefore, we have now two different systems, and you can send data to either one or the other, and there are also scripts which can be used to send or to get data from here and to send it to there. For the sites, for the data centers, there are three different models. There's a basic site, there's a standard site, and there's a premium site. So the big difference is that these are the standard data sets which all participating sites should offer. Then there is an additional possibility so that everything what the field system already offers can be automatically sent. And there is another specific thing which is very, let's say, essential for control centers, like if you control it with Wettzell different radio telescopes at one location, so we have an additional monitoring system. I don't want to talk about these two things. We talk about this basic side. So here you don't have to install any software, and here you have to install the software. So let's talk about this. So it's a basic monitoring with this elementary data set, and you have a basic monitoring screen, and you have this simple data injection. If you want to get more information about that, I will show you later some web pages where you can get additional information. Just to give some impressions about this, let's say, data access points, and especially about the web services. Here are some screens which are available on these different systems. The first one is this world map, where you see the current status of the site according to what is sent. So there are different trigger levels and trigger points, so that some alarms can be sent or can be started, and that you get the information about your network. Another thing is, if you use this standard model of the field system, you can get a web page which shows you all of the screens from the field system on the web browser. And another thing is what we use at Wettzell. For example, if you have a control center, you can get a map of the observatory so that you see the different locations, and you also can have some images of the telescopes so that you have a continuous overview about your systems. Okay, so another thing is the continuous or seamless data request. There is a Python script called sapix API.py, and you call it with different parameters. You can call it with a Windows system or with a Linux system, it doesn't matter. And you give a special configuration file, for example here for the EVN monitor. And if you, for example, just give the argument -L, then you will get the list of the participating so-called hosts. Hosts are the participating sites, though they are standardized in naming. This is the site name. The 000 is always a continuous number, so that it's lexically ordered in the whole list of all hosts in the monitoring system. And then there's a name of this this host. Okay, so if you request data, it looks like this. Use the same program, this sapix API, and then this configuration file. -L means list, and then you select the host. For this case, for example, JIVE on the EVN monitor. Then the key is the item or the value name of the current value which you want to get. So in this case we select pressure, and then you select the time interval, so the start time and the end time. And then if you run this program, you will get a list looking like this with the timestamp, the Unix time, so continuous time, starting at 1st of January 1970, 0 o'clock 0 second or minutes 0 seconds. So it's continuous Unix epoch, and then the value. Okay. A specific thing is that the value just has 4 places after the floating point. So this means everything must be shifted. This is a special thing in this SAPIX system, but the rest is quite similar to all values. So it's just a standardization. And then you get this list, and you can use this list, this data for your processing. So as I said, I want to give you some additional information. So if you're interested in more details, have a look at this YouTube video about the IVS Seamless Auxiliary archive, and also the Technical Operator Workshop contribution on my YouTube channel. Okay, so here are the links. You can select them and you can get more details, how to set up such system, how to send in data, how to get data, all of these things. So this is the current status. So we have 2 servers, one in Twingalo, one in Wettzell, and we run both of these systems. And now I want to show you a few of these benefits of this new technique, of this continuous seamless auxiliary data. First of all, if you have continuous data, it's easy to directly detect if there, for example, clock jumps or some errors. So changes, errors, if something happened. So in this case, we have something like a clock jump or something like that. So there's not a continuous rate or continuous timeline. So therefore, you can have a look at it. You don't have to request information from the sites. You just look into this web page, and you directly can select with drag and drop or with selection mechanisms which interval is of interest, and then you get this information. So it's an easy management. Another thing is you can use this data for cause research, because the data are collected and they are stored there for a special time period. In our case, we stored it for 3 months, and then they're copied to an archive. So only the important data or information are copied to an archive. But within this time period of 3 months, you can get information also about logging, about status of antennas and things like that. It depends on, of course, what the antenna sends in. So in case of the Wettzell antenna, for example, for the Vigos antenna, we received a week ago this message from Haystack. So there was the information that there are 15 minutes missing. So there are no fringes for special scans of 15 minutes. And there was the question, what happened there? So you can open the web page again, and you get all of this information from, for example, from the antenna control unit or from meteorological sensors. And then you see that there was a wind stow alert. So we had a wind speed over a special limit, and therefore the antenna automatically decided to go to a wind stow position to be safe. And then after 20 minutes after this wind, or after this gust, we change back to normal operations automatically. So this was logged in the protocol file or in this protocol of the Seamless Auxiliary Data Archive. And then you can have a look into these continuous data sets, and you see that there was really a wind speed of 100 kilometers per hour or more, and that the antenna started here to go into this special prevention of damages. So therefore it helps without any interaction. It helps to detect what happened And if you directly have access to this system, you can directly have a look at it and you can directly check what happened. Okay, so causal research is a very important thing. Another thing is the supporting of quality for correlation and analysis. So what I did is I used here a special intensive. So it was the intensive I-22074. So this is this time period starting at 1830, and it's a legacy system. And what you see here, the black is the continuous Dotman, so the continuous GPS minus FM out. Then the red one is a 6-hour period around the observation of 1 hour. The green is the special time period or the selection from the log file, so the special auxiliary data which you find in the log file. And the blue one is the special time period only for the observatory, only for the observation, but taken from the continuous data set. Okay, so if you zoom in, it looks like this. And what I did is I just calculated trends, so linear trends or one polynomial with a degree of 2. And if you watch this, there are differences. So there are different drift rates. And especially in the legacy system, it's quite important because you don't have so many scans. So if you watch this green line here, this is the trend line from the log file. And if you watch the blue line here, this is the trend line from the continuous data set. And the rate is completely different. So therefore, it tells me that maybe with the continuous data, it would be possible to get the clock parameters. And therefore, we prepare now some scripts so that maybe also the VGOSDB files can be created from the continuous data sets so that the correlators, the analysts can directly use them. This was the legacy system. If we watch the continuous trend, so this is the continuous trend over 3 months, you see that there is a drift of our maser, so the microphase stepper is set to a special level, and you see this trend. In our case, we use the EVOS 39 together with a GPS receiver Symmetricom sync server S250. So this was the legacy system. If we watch into the same time period on the VGOS system, it looks much better. Why? Because we have so many scans. Almost each minute there's a scan, and almost each minute you have also a clock parameter, so a Dotman parameter. And therefore, it looks quite similar. Nevertheless, with this continuous data, you can better do interpolation, polynomial interpolation of the trends, of the daily trends, because you directly have them available. Okay. So in this case, you get also a trend line. In our case, we use the EVOS 60 and a newer GPS receiver from Microsemi sync server S650, and the microphase stepper is adjusted in a much better level, and therefore you have a continuous line here, almost a continuous line, and also you have this continuous setting. Another very important thing is that the EVOS 60 is in a air-conditioned cellar, so therefore it's much more stable than what we have at the legacy system, and therefore the trend lines are much closer together. But it's nice to have these possibilities and to have a look at it and to play with it. Another quite nice thing was that with this data, we were able to support other disciplines or other researches. So, for example, there was this explosion of the Tonga volcano on the Tonga island on January 15th of this year, and this explosion started a pressure wave going around the world, and this pressure wave arrived on the different sites, sending the pressure values to the Seamless Auxiliary Data Archive. And what you see is the different arriving times of this pressure wave. So for example, in Agur, which means in Argentina, the pressure wave arrived at about 1400. In O'Higgins, it arrived at 1233. In Wettzell, it arrived at 1933, and at Medicina, it arrived at about 2009 UTC. So with this, it was possible to calculate the speed of this pressure wave. So for example, if you take the timestamps from the different locations in Europe, so Medicina, for example, and Wettzell. So thank you for supporting this, Pepe. So we can calculate that the pressure wave required 27 minutes and 39 seconds for about 523 kilometers on the Earth's surface. And what does it mean? If you use this data, the pressure wave had a speed of 1,135 kilometers per hour. So it's really fast. It's almost the speed of sound, okay? So, of course, you can check this if it is really what other researchers got. So if you compared with the Royal Meteorological Society, they had an article about this event, and they name the speed with 350 meters per second. And if you calculate this, so it's the same. So therefore, it's a nice add-on what you get here. What I also found out is that you need 1 minute intervals or 1 minute update times of these data, because otherwise you have a lot of jitter. But it's a nice outreach or a nice additional supporting mechanism. Okay, so what you saw is we have now a working system. There are benefits, but the benefits are not used at the moment. So there are just a few guys using things, for example, at Wettzell for the photogrammetry, or for local surveys of different teams in different projects. So therefore, in the summary, we have to say that it's a functional system. We have it at Wettzell and at Wingalo. It's, I would say, very easy to handle, to send in data. Already 9 different antennas do this. So 3 of them are at Wettzell. They continuously send data to either Wingalo or Wettzell, or to both at the same time. We have these nice browser-based access methods and web interfaces, so they are independent from the operating system. We have a nice convenient data export using this Python script. You just request this Python script, or you download it, and then you can use it. Some first use of the data for special project is ongoing. So for example, in our case, we use this auxiliary data for surveying, for photogrammetry, so additional temperature sensors in the telescope, for example, and for quality checks. So thank you for requesting things, Bill. I will support this, of course. And we have, in our case, we have a permanent use of a station monitoring, of observatory monitoring at Wettzell. So it's our central monitoring system and also our alerting system, so that we got the information for an on-call service if there's something wrong in our system, so that all antennas run autonomously and we are informed by this system. And I think there are some nice benefits in this demonstration. So what is the final thing now? I have some some wishes. So maybe more participating antennas would be great to get more data. So therefore it would be more interesting for the different correlations and analysis centers. And also for the analyzing correlation centers, it would be quite nice if you use this data so that we really see if there's a huge benefit or what is the real benefit in the complete data chain. So these are the two things, and also we should talk about which data are additionally important beside metrology and clock, and what are the data rates and things like that. So this is my presentation about the data. So thank you for listening, and we will see each other again in the next workshop, maybe online or in person. So have a nice time, and we'll see each other.